Welcome to Upstack America's IT training programs. My name is Bob and I'm the IT training lead for Upstack America. Today's training is on data science and specifically on artificial intelligence and machine learning. Our trainer will take us through today's session is Paul DeBacker. Paul is a data scientist with outstanding work experience managing digital transformation projects on artificial intelligence and machine learning. He also holds extensive experience as a solution architect for robotics process automation, and also he has experience as a developer for robotics process automation. Paul holds a Master of Science in Artificial Intelligence and Machine Learning from the University of Texas in Austin. He also holds a first-class honors Bachelor of Technology degree from Anna University, Chennai. Thank you for watching and we hope you will enjoy the training.
All right, so today, session one of, so we will be touch basing machine learning today. So today's session will be more into the theory side because before we jump into any practical or hands-on, we should understand certain theories, which we haven't learned before. Right. So before we get started, Kevin, if you could just tell us about what we discussed on the last session. Where did we end up? And then we'll get started.
Last time we discussed about categorical encoding and normalization approach. We looked at different methods of encoding, which the label encoding, where we converted labels. We used the example of countries into numerical form. And then the next one, we looked at one-hot encoding, which is splitting the columns which contain numerical categorical data. Uh, we also You also said the label encoding is ordinal data and one-hot encoding is not ordinal. That was the main difference I captured there. Then we looked at normalization and standardization. Normalization, which was a scaling technique where values are shifted. Uh, he also mentioned standardization does not have a bounding range. We also looked at some libraries here, sklearn libraries and scikit-learn libraries.
Mhm.
You also asked me to remind you about high cardinality and curse of dimensionality when you get to models.
All right. Perfect. Perfect. Absolutely. That's great. So yeah, we will. I'll remember that piece. So when we get into our machine learning, hands-on, probably I'll check out the content for tomorrow, and based on that, I'll set that. So all right. Yeah. Perfect. So that was so till last week, what we learned, right, from the first day till last week was, I mean, see, it almost took us how much? Almost 8 9 sessions, right? So that 8 9 sessions, we only were able to learn certain, you know, preparation part. That if I want to do machine learning, what are the things I need to know? So all these prep sessions we learned, I would call this a prep session, statistics and everything, EDA and all these things, you're gonna see the applicability of all these theories that we have gone through from here onwards. So from here on, it's all the main black box that we talk about. That what is machine learning, what does machine learning do, how do we do predictions, what are predictions, and all those things we'll be seeing, right? Okay. So, I think in the very beginning of the session, we spoke about two things. When we had a session of introduction to data science before we got into Python, visualization, and others. So, there I would have explained you about what is artificial intelligence, what is machine learning, what is deep learning, how these are interconnected. Then we have seen on data science introduction, we learned about something called a supervised, unsupervised, and reinforcement learning. right? So those are the things which we're gonna come up right now. So whatever we learned on machine learning, the supervised, the unsupervised, all these things are gonna be a deep dive sessions. We'll be looking into more granularities of all those topics that we discussed. How does it actually happen and what are those, right? So what is an algorithm in machine learning? So we talk about two things in machine learning. We talk about machine learning algorithm, we talk about machine learning model. Now, to start off, we should be at a very good position to understand that what are these algorithms actually mean and do, and what is a machine learning model mean and do. Because uh, unless we have a pretty much deeper knowledge on the theoretical side, when we move on to the Jupyter notebook for practical implementation or into the coding side, it becomes tough to understand the flow, right? Okay, so what is an algorithm in machine learning? So it's an algorithm in machine learning is defined as a procedure that runs on data to create a machine learning model. Now, what does that mean? So let's say I have been given a data, right? So I have been given, let's say, the Amazon's sales data example that we take, right? I want to predict sales. Okay. Now I have my x's here. I have my x1, I have my x2, and I have my x3, and this is my target column, which we call it as y. Now, seeing this data, when I do some procedural steps on this data, and I define those procedures and I run on it, which creates a model for me, is what is an algorithm. And I mean, if you would have learned in normal engineering also, algorithms are nothing but, we call it as defined set of instructions or procedures, that okay, this things is gonna be having this as the flow. So something like that. So these are procedures that run on a specific data to create a model. So we run an algorithm on the data to create a machine learning model. Okay. Now, machine learning algorithms that we run on the data, what does it exactly do to create a model? So it does an important thing called as pattern recognition. So what does this algorithm is capable of? This algorithm is capable of doing nothing but do a pattern recognition. Pattern recognition means trend in the data. So we have spoken about what is a machine learning do in the definition. So machine learning helps us to identify the various patterns that are hidden inside the data. Like we saw the cardio data set, right? Where I had this different customer information followed by how many weeks they're planning to use and blah, 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 right? When we did an EDA with various libraries and steps, we were able to identify some hidden analysis that, okay, for my age bracket of customer between 30 to 40, they are using the treadmill very much higher, or my female gender in the data has utilized the product pretty much higher. So all these analysis that we come across, you know are nothing but the pattern recognition in the data. This is what a machine learning algorithm does. It tries to identify the pattern that is hidden inside the data. So an algorithm, what it does, an algorithm learns from the data or are fit on the data set. So generally what happens? So when we use a specific algorithm, let's say ABC is my algorithm. Okay. I'm not going into any names, will be pretty much generic now. So let's say ABC is an algorithm that I run on my cardiovascular data that I had, correct? It is the moment I apply this, it gives me some hidden patterns, right? It tells me what are the data trend that is telling. So what happened when I applied this algorithm on this data set, the the algorithm learned what is the data telling. Now this similar algorithm, I can pass it on to the other data set. Let's say we saw one automobile data set, right? With various parts information. I can pass this to this data set, then it will tell me what is the trend. So this algorithm will then learn what this automobile data is telling and then identify the hidden pattern inside it. So irrespective of my data, whatever I pass, an algorithm is capable of learning what your data is telling. That's the main impact of machine learning. So why we call it as machine and learning? Because my machine, with the help of algorithm, learns from the data. That's why it is called as machine learning. So I say the machine to go and learn using an algorithm that what the data is trying to convey, or what information that the data is actually having inside it as a hidden information. So that is what is an algorithm in machine learning. Now, what are the properties that we have for all these various machine learning algorithms? What sort of properties does it carry? Okay, so a machine learning algorithm can be described using map and pseudocode. So how do we define these algorithms? These algorithms are nothing but mathematical representation and can be defined by any lines of code or pseudocode. Now, pseudocode means dummy code. Okay, so let's say I want to find the if I give you two numbers and I want to find the largest number, I ask you to write a code in Python. So you know that there is a specific format of writing it. But when you give me any sample or a dummy code that, okay, this is the logic of the program, we call that as a pseudocode. So if I want to find largest number between two given numbers, what I'm going to do? So first I'm going to take first number in a variable. I'm going to take the second number in another variable, and then I'm going to check if first number is greater than second number, and then I'm going to just print out the result. Print greater number. So these four steps that I've written is called as a pseudocode. That means the logic or the sample code on which I can build up my actual programming. Okay, so but because these are not the proper syntaxes, right? I have to apply I have to apply an if, I have to give a colon, I have to do an indentation, then it converts into a program, Python code. Rather else, before that, if I just write the logic here, it becomes a pseudocode. So what is an algorithm described as? So we can describe an algorithm always in a mathematical space. We know that, whether it's a regression line, whether it's a fit curve, because what is this graph is nothing but it's a mathematical space, right? So that's where the representation of an algorithm comes in. Okay, yeah. Now the efficiency of machine learning algorithm can be analyzed and described. Yes. Now what is the efficiency, or what is the accuracy, or how accurate or how efficient is my algorithm? You know, we can analyze that, we can describe that, and we can measure that. Whether if I'm predicting sales, how much accurate is my model? Is it 90% confident on the prediction? Is it 95% confident on the prediction? It is 30% confident on the prediction? Is it 10% confident on the prediction? This accuracy is measurable content. I can measure using, when my model is running, that how accurate gonna be my model into production. So that's what is called as analyzing and describing an algorithm. Now, machine learning algorithms can be implemented with any one of a range of modern programming language. That means we use Python these days as a modern programming language to code this algorithm for implementation, or we use another language called as R. So both R and Python are statistically strong. R is considered to be more stronger than Python. It is also an open source language. It is more statistically strong and heavy, whereas Python is kind of a little easier, but still it is also pretty dynamic, pretty contentful. There is hardly anything that you cannot do in Python these days. Okay, So let's say if Python is widely used across in the world as, let's say, 80% for data science, I should not say 80, I should make it a 60. I should say R is also used for 40% of the activities in the world for data science, right? So this is how, your algorithms are written or implemented using different programming languages, right? Okay. Any questions till now, Kevin?
Oh, none so far.
Now, what this slide we would have already seen earlier, that in our data science introduction, that machine learning algorithms can be divided into, we have seen majorly into two different types. There are three, but we will focus on two. One is supervised learning algorithms, and another is unsupervised learning algorithms, right? Now, what are supervised learning algorithms? When I have my x's along with my y is given, remember? So when my x's are there and my y is given, we know that my data or my algorithm can learn the y within the data itself. Then we call them as supervised learning process, where I know my target column is supplied in the data, right? What is unsupervised? When I do not have my y or my target column given in the data, we call it as unsupervised learning. Now in the supervised learning, when we do with numerical problems or continuous data, or kind of a, when we want to, identify some trends, some information on the numerical side of it, when the model relationship becomes a scalar response, right? Let's say when I want to define my model in the form of an equation of a straight line kind of a thing, y is equal to a plus bx. What is this? Y is equal to a plus bx. This is the equation of mathematical equation of a straight line. Straight line, right? So when I have a linear equation developed, we call it as regression, right? Else there is another problem where which we deal with called as classification. When I want to classify something, I want to say whether I am a good or a bad person, right? Whether I am a I'm a good customer or a bad customer kind of a thing. Whether the image is given of an important is a dog or a cat, we classify them. Then we go into neural network of deep learning, that is a different genre. And unsupervised, what we do this clustering piece. We cluster and try to identify that majority of the data points falls into which cluster. So the moment I draw a cluster, I find, okay, my data has three distinguished clusters or groups. One is green, one is represented by red, another is represented by blue, although there are certain overlaps that are happening across my clusters. So we will see supervised learning algorithms. So our first focus will be on supervised learning algorithms for next 2-3 sessions at least, and then we will go into unsupervised learning, where in supervised we will see in detail about regression algorithms, we will see about classification algorithms, and then we'll switch to unsupervised learning, where we will see various clustering algorithms, how it happens. All right. Next. Now, after we know that what is an algorithm, we should know that what is a model. What do we call a model? So a model in machine learning is nothing but the output of a machine learning algorithm that you run on the data. So whenever I have an algorithm ABC applied on a data set, okay, to find out the hidden pattern or hidden analysis, and it gives me a result, or it gives me an outcome, we call this as the model. Okay, so we call this as the model, that this is what my algorithm's outcome is, and the machine, the machine has learned this from the data and giving me this as an outcome, which is nothing but the result, or we call it as model. A model represents what was learned by a machine learning algorithm. That's what I said. So whatever, if I'm giving a data and it is giving me a result, now this algorithm is passed on to a data, and then let's say this data is telling me x is equal to 2. This x is equal to 2 is actually a model. So whatever my algorithm learns on the data and gives me output, we call that output or an outcome as the model. Okay, now if I give this data into this and it is telling me that, okay, your, if let's say this was my cardio data, it tells me that your female customers are buying your product higher. So this outcome which the model, which the algorithm is giving me, is known as my model. So model represents nothing but what your machine has learned from the algorithm. That's what is called as a model. Okay, now, a model is the thing that is saved after running a machine learning algorithm on training data and represents the rules, numbers, and any other algorithmic specific data structure required to make a prediction. So, what does this model learn actually? So, whenever we have this algorithm that gets applied to a data set, what does this exactly algorithm learns? The algorithm learns, first one is hidden patterns. Second, if the data is having any specific rules. If the data are anything at a number specific analysis. And fourth, it tries to identify certain data structural attributes also. So these are my various outcomes, or these are my various learning parameters that an algorithm learns from a data set. And combining this, when it gives me a result, we call this as a model. So this is what a model is all about. So algorithm given on a data set
Hey,
learns
Bob,
and gives me, yes, tell me.
could you list those four items again, please?
Oh, okay. So one would be learning your hidden patterns, right? That's what we have understood. So learn the hidden patterns of the data. Second, if the data is showing, if what are the rules based on what are the hidden rules, or is there any rule based on which the data is explaining something? Third, whether there is any number or trend in the data. So let's say whenever your data tells you that, okay, in 2020 your cell was down, but in 2019 your cell was up. That means the trend is like this. So all this trend that you draw in a Python is nothing but a model's analysis, right? And fourth, it tries to also identify specific data structure related attributes. What is your data talking about? So that is completely into data structure part. So these are the four parameters, or let's say uh, facts or artifacts on which your model, sorry, your algorithm learns from your data and gives you an outcome as a model. Clear? Any questions?
No, thank you.
Okay. Next. Now, so now we have learnt about machine learning algorithm. We have learnt about what is a model. Now we would be seeing a very, very keen, very important and core concept of machine learning called as what is model training. So we know what is machine learning, right? So we have already seen a definition of machine learning in our exercises. Whenever a machine learns from the data around the world, we call it as machine learning. And utilizing that learning, when a computer or a system does anything smart compared to or equivalent to human intelligence, we call it as AI, that is artificial intelligence, right? Now, what is model training? We have spoken about model, which is an outcome. We have spoken about algorithm, which is applied. We have spoken about data set. We have spoken about EDA. But how does your algorithm learns all these attributes, all the hidden patterns, all the hyperparameters, sorry, all the rules, all the trends, right? So the outcomes, when the outcomes are nothing but the algorithm gets trained on a specific number of data, right? So what is a model training in machine learning? So it says that if you evaluate your model on the same data you used to train it, okay, your model could be very, okay, so I'll come to this statement later. I'll explain the diagram first. Now what happens here is, let's say you have a bunch of information. Okay, so if I let me divide this. So let's say this is my past and this is my future, right? So past means what? Whenever I take a data which is historical data always talks to me about the past, correct? That means what has happened in the past. So the cardiovascular data we saw was a historical data of my company's product. So what has happened in the past, right? With this historical data, I want to predict my future, that what is going to happen, correct? Going to happen, right? Now, the past that I have on the historical data contains information and also something called as noise. Now, why I say noise? So, whenever you pull any business data, you will definitely have data which are good for you, and you will definitely have data which you don't need. So, all the data that explains you about something is all your information, and the unwanted data that you get is called as noise. So machine learning is all about looking at the past, making the assumption that at least a part of the past will repeat itself in future, and that's what we call as information. We need to create a mathematical model to understand my historical data that captures only this information and not the noise, and then tells me what is going to be the information which explains me the future. Even what happens when we take this information, ignoring the noise, and we put it in a model and try to predict the future, the model still contains some information and noise. It still takes some noise. Why? When we see bad predictions, right? When you see that your prediction accuracy is 30%, 10%, like 50%, that means what? Here more 70% accurate is your prediction is incorrect. Here 90% predictions are incorrect. Here 50% predictions are incorrect. That means though your model took only the information to predict the future within another set of information, though it ignored this noise, it carried some sort of a noise still with it. That's why it is making bad predictions of 30, 10, and 50%, where remaining percentages are your bad prediction or inaccuracy of the model. So the information that it carries from past to the future is same. I'll just clear this. So if this is my past and this is my future, this is information and noise, this is information and noise. So this information and this information is the same, but you have ignored the noise, but it still contains some noise because it is making bad prediction. That means, but this noise is not this noise. So this is a new noise which the model would have miscalculated or misprogrammed within the data or the information that it has carried. Okay, now if this is the case, now what is meant by model training? Now let's say I have a data which is this cardiovascular data. Okay, now this data is completely, this data is 100%, which is explaining me about my customer information. Now in machine learning, what is the hard and fast rule, or what is the fixed procedure to train? Now how do my algorithm learn the training? I mean, sorry, how do my algorithm learn what is there inside my data, right? To do that, we train the model. That means I say take the data, put it onto the algorithm so that the algorithm gets trained and gives me an outcome, which is the model. Now, what is a training test? What is a training set and what is a test set? If you see here, if what is being explained here is, if this entire block is my data, which is 100%, okay, what we do is we split this data into 70% and 30%, which we tell that I split this entire 100% data into 70-30 ratio, okay, saying that from this entire data of my whatever customer data or whatever is the data, I will use 70% of my data to train my model. That means using this 70% of this data, my model will try to learn the hidden patterns, the rules, the trends, and everything. So this 70% of the entire data I will use to train my model so that it understands all these three factors. Now, how do I test that whether once I have trained it, let's say it is giving me an accuracy of 90%, that it has able to understand all these rules, trends, and hidden patterns. And the model is telling you that I'm 90% confident to give you an outcome on your cardiovascular data set, right? Now, how do you validate it? You know that, okay, you have supplied the data, you have trained it, but you need to test it, right? Whenever we create a software, we do a testing, correct? Whether the software is accurately working or not. We have unit testing, we do user acceptance testing, we do black box testing, we do why. These are all software development testing. Anything that in the world that's created, there is a measure of test, right? We test certain things. Even the vaccine which got created, it was tested. The sample dry run was run on, or human trials were run to test. So they created a specific solution, which is a vaccine to fight COVID-19, but they wanted to test the outcome. They know that this vaccine in the laboratory has given me this much accuracy that it kills COVID-19 or damages COVID-19. But how do you validate it? You apply it on humans, on a vaccine. In machine learning, how do I validate it? I apply this model training into a data to test. Okay. Now, if I'm asking my model that let's say I've trained my model to learn addition. So I've trained him asking 1 plus 1 is equal to 2, 1 plus 2 is equal to 3, 1 plus 5 is equal to 6. Okay. 1 plus 6 is equal to 7. Like this, I have trained with 70% of my information. Now, how do I test whether it is doing right or not? So I use 30% of my remaining data to test. Now, after this, I will give him, okay, 1 plus 4, tell me what is it. This 1 plus 4 is not a part of this data because I have splitted the data into 70% of into training, which is unique data, and 30% into testing. So this split is dividing my entire data and there is no overlap. So whatever data I expose to the model for training, I never expose it to the data while testing. So this test data that gets created in a machine learning model to test what your model is exactly learned is called as the test data set. And this test data set is never shown to the model while you train it. So that means we isolate this data completely using Python from my entire data. So let's say I have a data of 100 rows. So I'll take 70 rows to train and I'll remove 30 rows from there, which I'll keep it separate. So once I train my model on this 70% or 70 rows, I'll call any one of these 30 rows to test whether it is working fine or not. So remember one thing, the training data and the testing data is the core concept of machine learning. So I split always any exercise that you take. You have to split the data to train your model and then test your model. These are the two basic and comparatively the ground rules for machine learning. So now what we generally prefer, that this testing data that we split out from the entire data is never exposed to the model while I train it. Because if I expose this data, the model will already understand what is there, what is the pattern. So what is the use of testing? So that's why they say that training data is where the model gets trained on and gives you a certain accuracy, and the testing data is where you test the accuracy of whether If it is giving you a 90% accuracy, you need to validate, right? Then you pass this test data to the same model which you trained and then check what is the accuracy. Now this accuracy can be 92%, which is more than your training, and this accuracy can be 50%, which is less than your training. So when I train my model, let's say my training accuracy is 90%. Then when I use the test data and try to see what my model is doing, my model accuracy is 92%. So what does this mean? So when my training accuracy is less and my testing accuracy is more, I am sure my model is doing more perfect, because this unseen data the model has not seen while I have trained, but it is still predicting with the higher accuracy. That means whatever I have done on my data EDA was absolutely correct. I am more confident that this model will be working perfect in production. But next, what happens if my training accuracy was 90 and then when tested it on a testing data, my accuracy dropped down to 70%. My model is making bad predictions. That means it was trained well, but when I tested, there are some unknown data or unknown patterns that was available in this test data, which the model did not find on the training data. That's why it failed with the lesser accuracy. It did not fail, it predicted, but it is only 70% accurate. That means when my training is higher and my testing is lower, we don't take those models for production, at least to a marginal gap. 70-90 is huge. If my training is 90, okay, and my model and my testing accuracy is, let's say, 89, this is still fine because it's quite near to my training accuracy. That means in training I was 90% confident of predicting something. In testing also I'm 89% confident. I can still look into my data and see if I make some adjustment to increase this by 1%. So this is what is called as model training. So remember, in machine learning, we take the data, we split it into a test data and a train data. Training data is applied into the model algorithm to understand what is exactly happening. And once it is trained, I then pass on my test data to the same trained model to do a prediction outcome and see how much accurately it is predicting on an unseen data. Okay. Any questions on this, Kevin?
Yeah, Paul, I'm trying to understand when you say you split the data, say for example the automobile data, we got it as a whole data set. Are you saying we split that data or we use that data and then create another set for the test
No,
data?
no, no. We use the same data. We use the same data. Let's say that automobile data has certain columns and certain rows, correct? So
Yes.
from that entire corpus of the data, we take 70 this is a standard ratio in machine learning. We always take 70%. I mean, it is not hard and fast, but the standard is 70% to train, 30% to test. You can still make it as 85-25 also. That's up to you. Okay, you can make it as, but nothing below 70. At least 70% you need for training and 30% you need for testing, or you take 80%, 85% for training and 25% for testing. Right now, this automobile data which is there, it has certain columns, right? X1, X2, X3, X4, and let's say Y, and it has some values here, right? It has values here. This is my how my Excel data looks like, correct? Right, this is my data. Now what I do here is, what do I mean by testing a 70 and 30 training testing is, from this entire data, using Python, we have some libraries in scikit-learn or sklearn, which will split this data into random ratio, which will take this data and split it randomly into 70 and 30. So let's say I have let me tell you this way. So 70% training and 30% training, right? So let's say I have this much data here. So I have my X1, I have my X2, I have my X3, and this is my Y. Okay. So let's say these are my some values A, B, C, and let's say I'm predicting X. Sorry, I'm predicting 0 or 1. It is 0. Then I have D, E, F. I'm predicting it is 1. Something. I'm just giving an example. Let's say again it is G, P, M, and I'm predicting it as 0. Okay. Then let's say I have T, K, P. I'm predicting it as 0 again. Let's say it's N, S, K. I'm predicting it as 1. So let's say these are my some X's. Okay. And this is my Y. This is my, let's say, data. This is how it looks like in Excel, right? So when you pass on this data into the Python library and made it to 10 and test split. So how many rows I have here? I have 1 row, I have 2 rows, I have 3, I have 4, and I have 5. So I have 5 rows. So what it will do is, out of these 5 rows, it will randomly take 70% of the data. That means either, if what I'll do is basically I'll break it here. Let's say if I have to tell you very hypothetically, let's say 70-30 means I break the data here. Okay. Now this portion of the data is 70%, which I use for training. Okay. And this remaining 30%, I use it for testing. Now, when my model trains that A, B, C is actually 0, D, E, F is 1, G, P, and M is 0, this is for training. What I do is, in my testing, I know that T, K, P is 0 for me, N, S, and K is 1 for me. So when I test it, I will not supply this Y actually. Okay, these Y's are never supplied in testing, only the X gets supplied after I split it into 70 and 30. Then when the model takes this and based on this training, it gives me an outcome. Let's say it gives me the outcome of this combination as 1 and this combination as 0. So this is my prediction. But then when I see my actual data in supervised, I have my Y given. Then when I map that, no, that means my model is predicted incorrect, because actually this is actual, this is predicted. It should be 0, but it is 1. This should be 1, but it is 0. That means my model has predicted wrong. So that means my model has poorly performed on my test data. That means whatever I trained it, it was not sufficient enough for my model to predict something like this. That means the training happened, but the training is not that useful. So let's say I train you on Java, and then I give you a problem to solve on Python. So what does that mean? You will fail, right? So that means whatever was taught to you was Greek and Latin, and then I'm asking you in, let's say, Spanish or in German. That means whatever was trained, what you trained on the model, it was not enough or sufficient, or something different would have happened, that when you applied the test data, it failed to predict. But instead, when I train it, let's say for 0, it predicted also 0. For 1, it predicted also 1. That means whatever I used here to train was, my model was able to depict the patterns and the rules that it was able to predict this combination and give me an output. So you will get to know this more later when we go into hands-on and also things like that, how to split, how do I do the prediction, how do I train it, how do I find which is my predicted, which is my actual, all these things will be more clear. But as of now, is the core concept clear to you, or you still have any doubt?
No. That's more clear now. Now I get the concept.
You got the concept, right? So training and testing means on the same data, when you use a library, the library will randomly take 70% and split remaining 30%. It will do randomly. We have a parameter that we pass as random, because if I don't take random, what will happen is it will not take serial by, like let's say if I have 100 rows, 1, 2, 3 till 100, it takes 1 to 70 for training and 71 to 100 for testing. It doesn't happen. I mean, that's not a good exercise in machine learning. So what the library does is, from 1 to 100 rows, it will randomly select 70 rows. That means it might select 1, it might select 20, it might select 21, it might select 100, it might select 90. Like this randomly, it will select 70 rows that will go for training, and remaining 30 which is there will be again utilized for testing. So that means once you segregate, so let's say if I have this data here, okay, I take out randomly 70 balls, remaining 30 balls are here, right? So automatically when I take out the training set, the remainings are used for testing. So that's how it splits. It's, you can imagine it is like you have a bucket with 100 balls, you take out randomly 70 balls which you will train, and remaining 30 which is there in the bucket is your testing data. Got it? Clear, or any questions?
No, that's clear.
Right. Now, training set versus test set. The war is still not over. So training sets are used to fit and tune your models. So when I say fit, it means it's a programming language. We say the model is fitting. That means that the model, we are fitting that model on the data. Like when I say that, okay, I'm wearing a t-shirt, it's fitting me. That means the size of my body or the size of the t-shirt is fitting my body, right? So similarly, when your model, when you say that your data is fitting on the model, that means we are applying that data to sit on that model, and that so that the algorithm can make predictions. So training sets are used to fit and tune your models. Tune means, let's say, fit means when I put it to train. Tune we will come it later. Tune means if it is doing very wrong prediction. Let's say I am wearing a t-shirt, I take the size as large, but the t-shirt that I wore is what? Small. So what I'll do, that means that t-shirt did not fit me. So I'll go and change it. So tuning means changing. So when my model is making a bad prediction, that means it's a bad fit. I tune my model. That means when you go to a shop, you try out various sizes, right? If you want to buy a t-shirt, you will try this size, that size, and go into the mirror and see which one is fitting you. You take 2 3 sizes with you of a specific brand if you are not sure, and see which one fits you, and then you decide. Similarly here, when you put a data on a model, okay, the model might not be able to fit on it properly. That's when it makes bad prediction. So when you see it is making bad prediction, that means like a wrong size, you go and you try various sizes. Then in tuning, we try various other approaches to see if it is fitting. That's what it's called, tuning. It's a separate domain. I will talk about it once we go ahead, right? So training sets are used to fit and tune my data or my model. Tests are put outside, which is unseen. That's what. So remember very, very clearly that whenever your test data is created, your test data is always unseen to the model, because when you train, your test data is never passed. That's completely discarded, isolated, so that I can then test on my unseen data to evaluate my model. That's what we have just exercised or known. Now, you should always split your data before doing any analysis. That's the trend. So after your EDA is done, the next thing before you get into a machine learning model is to split your data into training and testing, which is 70:30. This is the best way to get reliable estimates of your model's performance. So you train and then you test. After splitting your data, don't touch your test data set until you are ready to choose your final model. That means once you are training the data, now let's say I have my training data ready. This is my training data and this is my test data. Now, if let's say I have applied algorithm one, sorry, the model gave me outcome is model 1, which is 30% accurate. On this data, I applied algorithm 2. I have an outcome is model 2. It give me 60% accuracy. I applied algorithm 3. I got model 3 giving me 90% accuracy. So what it is telling is that once you don't touch your data unless you are confident or you are ready to choose your model. So when I am training my data on 3 different models, so when I saw that, okay, model 3 gave me a 90% accuracy, then will you take 30 and 60? Obviously no, right? You will discard these models. Then you will take this algorithm 3 and then apply it onto your testing data to see what is your accuracy. If that is also giving you, let's say 89% accuracy, then you will understand, okay, your predictions are correct. So that's why it is saying after you split the data, do not touch your test data until you are ready to finally choose a model and then test it. Okay. Now comparing test versus training performance always allows us to avoid overfitting. We will see what is that definition is. Now, there are two concepts about model training. So when we talk about model training in machine learning, there are two vital concepts. One is called as overfit, okay? One is called as underfit. Now, if I give you the example of the t-shirt size that you are talking. So when you take a size which is larger than you, let's say you fit into large, you took XL, extra large. So that means it is overfitting you. That means you have a specific size, but the size you took is more larger, right? It overfits you, right? But if your size is larger and you take a medium size t-shirt, so when you wear it, it will not fit you. That means it will be more tight. That means you took something which is lesser than your original size. So that means it underfits you, right? So that's the same concept here. So when a machine learning model is failing to understand the underlying trend of the data when I train, okay, that means my the model is not able to understand the data well, we call the model as underfit model. So when I take a 70-30 split, okay, 70-30 split, this is my training data, and then I train my model, okay, and then I test my model. Let's say my training accuracy is coming as 80%, okay, right? And my testing accuracy, give me a sec. Yeah, and my testing accuracy is also, let's say the model training accuracy is, let's say 30% or 40%, okay? So when you train your model, you get a training accuracy itself as 40%. What does that mean? That means that when your when your model is trying to fit in that data, the model or the algorithm is not able to understand the data trends available in there. It is not able to recognize anything. That's why it is giving you a bad training output. So in that case, we say that your model is underfitting. Now, what is an overfitting? So when your training accuracy is, let's say, 90%, and your testing accuracy, when you apply it on a test data, your accuracy comes down to 75%. So when your training accuracy is higher and your testing accuracy is lower, then means your model overfits. That means it learned everything in training, but when it is tested, it is failed. That means you are coached perfectly fine on a subject, but when I took your exam, you failed. So that's the evaluation metric of a model. Similarly, so let's say I have taught you for 6 months data science, then I took an exam. So I've trained you. When I was teaching you, you responded well, you understood, you said you got to know concepts clearly. So and your training accuracy was, let's say, 80, right? Then I said, okay, Kevin, I'm going to test you. So I kept an exam, and then I kept some questions and then asked you. That means I have taught you so many concepts over the 6 months, which went into your brain. Similarly, how a model learns, right? It got fed into your brain. Now, concepts which doesn't get into your brain, clearly you don't understand the specific topic. That means you are underfitting that topic. Your training is going bad, right? Now when you say that, okay, you are understanding everything in the training, yes, Paul, I got this, that means I trained you with all the possible data that I have or the information I have. Then I said, Kevin, I'm going to test you. He said, okay. Then I said, okay, so I give you some 10 questions. So when I trained you, I give you a data or I give you information which is this 70%. Then when I took your exam, which are where you got some unknown questions, unseen, which was not as part of your training, which was this 70% which I taught you for 6 months, was not there. This 30% does not fall in that 70, right? So when I take your exam with 30% data, that means I give you 10 questions. These are where unseen questions for you, right? But those questions which are unseen to you, when you get a known question, that means that question we have discussed, you will be able to answer better, right? Because that question of your test matched, or you identified that, okay, your brain identified, oh, this topic was taught by Paul. Oh, he told me that if there is a y given, it is supervised learning. So if I tell you what is the rule of a supervised learning, so what will be your answer? You'll say if your y is given, target column is given, it's supervised learning. Now when you see that question which was unseen to you when we trained, and then you relate, okay, that was taught in my training, and you answer that question, what happens in your brain? It's a pattern recognition. Your brain was able to identify that this question matched with the question in your training, so you go and answer it correctly. Now let's say if I ask you what is reinforcement learning, this question your brain did not know in the training. That means I would have missed training you on reinforcement learning, so you are not able to answer that question in your test. That means that your training did not happen on that specific question. So similarly, if your model makes bad prediction of a specific data in the testing, that means that pattern which came in testing was not available in the training. So in the testing data, the model got some new pattern which it was never aware of before. It was not trained on. That's where your model goes wrong. So there are multiple ways to ensure, which we will learn further, that how do I capture all the trends that I don't miss on my training, so that whatever unknown data I give it to my model, it is able to predict properly. That means my 70% of training has to cover majority of my patterns of that specific data that I'm giving. Only then this 30% will be proper. Now, let's say I also trained you on a topic, but the question that you got was indirect. Okay. For example, let's say I have told you that whatever I have told you, you did not get a direct replication of the question, but you got a different question. But your brain is able to conceptualize, okay, so Paul said if supervised learning, let's say I taught you on supervised learning, that supervised learning means your target column is there. That was your training. In exam I have asked you what is unsupervised learning. So what do, you think, you try to conceptualize. So if supervised learning means why is there, then might be unsupervised learning means why is not there. You go and write the answer. So supervised learning means when your target column is not given. That means though I trained you on supervised learning, I gave you an answer, your brain conceptually calculated that unsupervised should be this one because supervised means this, and you write the answer. So your brain is able to decide based on what you had trained. Though you are not trained directly on unsupervised, but some relevance was there. Some pattern was taught from where you depicted your answer and wrote. Similarly happens to a model. Not all underlying patterns are captured by the model in the training data. So what it does in testing, if it finds a relevance pattern, so all these models are intelligent enough that even though it finds a relevant pattern in the training, it will be able to predict in your testing data, like the way I have explained you with the unstructured and the structured question. As your brain finds to conceptualize what was taught in your training and then find some relevance answer for indirect questions, your testing or unseen data might have scenarios which were never caught or direct trained in the or never captured on the training. But the model is like a human brain because it is, that's why it's an intelligent machine. So it is able to understand that, okay, in training I would have got x plus 1 is 4. Now I have got y plus 1. Okay, so let me write something to it. So that's how your model evaluates at the back end. And then once it is trained, it goes on testing. So now this is what we call it as overfit and underfit. Is it clear or any questions? Very, very important topic in model. Interview, you get 2-3 questions on this. What is your model overfit? What is your model underfit? What do you do when your model overfits? Though we haven't seen how to eradicate it, we will see. What do you do when your model underfits? All these things are there. So is it clear or you have any questions?
Oh, your example got me scared. I haven't seen my results yet.
Sorry?
I'm saying
So that's what I'm saying. So are you able to relate how a human learns or how a human conceptualized through brain and how a machine conceptualized through training and testing? Able to understand it or not?
yes, I can understand that.
Okay. So when we go into deep learning, which is advanced version of machine learning, so we will learn that how like a human brain we have neurons. So each neuron in a human brain is able to predict or tells or decide. Similarly, we are creating artificial neurons on the machine, on the data, on this using algorithms, which takes intelligent decisions like human. So let's say when I give you an image of a cat, you are able to see. Next time when I give you an image, or whether it's a cat or a dog, you will be able to identify. It's hey Paul, it's a cat because I've shown you images of cats before, so you know. Then if I show you a cat image of a dog, you'll say no, this is not a cat because you have already been seeing how a cat looks like. Similarly, when you give an image to a model, how does the model work? Right? So I train the model on images of cats and dogs. And then when I give a new image, it is able to tell me, no, it is a cat. No, this is a dog. No, it is neither a cat nor a dog. How does it decide? So it utilizes human underlying brain concept of neurons, which we call it as artificial neurons that we develop so that my machine is as intelligent as a human. Right. So I think we are top of the hour today. For you have to catch up, right? So we'll just wrap up with this. Yeah. So we'll just wrap up with in the next 5 minutes. Hope that's fine, right?
Yep, that's fine.
Okay, 5 to 10 minutes we'll wrap up. So, what is your model underfit and overfit? So, what did we understand that in case of an underfit, my model fails to learn the hidden patterns of my data. It doesn't know what the trend. So, if you see an underfit graph, see it is flat. It is flat with respect to my x1 and x2. This is flat. This is how an underfit graph looks like. That means it is not able to see whether it's an increasing trend or it's a declining trend, it's a zigzag trend, nothing. You know? But so what does an overfit look like? Right? So overfit means it was trained very good, but when I tested it failed. Right? So in case of overfit, sorry, okay. So instead of overfit, so see, for an underfit, if these are my data points, okay, if these are my data points which I have to predict, see the line is flat. That means it did not capture here, it did not capture here. It only understood these 2 points somewhere. So majority were uncleared or unanalyzed. So that's why it's a flat line. So if I have to see that this line with respect to these points, it is error. So the distance of this point to this line is bigger. So my error is more. When I say overfitting with respect to x2 and x1, it overfitted. That means trained very high, but when I tested, it failed. See the graph, it is zigzag. You know, it learned something good, but when I tested, it failed. So it was able to cover all the dots in training. See, I'm going through all the data points, but it is a with certain error parameter. So what should be an optimal training look like? An optimal training should look like this. So this is a perfect fit. So if I have to see that my model is 90% accurate, and that means the fit has to be optimum. which is somewhat like this. This is how the curvature goes. So here also I have misclassification, but see, the distance from here is low, the distance from here is low, the distance from here is low. That's why I'm saying it's 90% accurate. That means for these 3 dots, it is misclassifying. But with respect to my pattern of understanding, it is able to learn the proper curve. So these 3 dots would represent my remaining 10% where the model might fail. So this is how you compare your overfit, your underfit, and your optimum. So we will see now what is your overfit is also not good, your underfit is also not good. So how do you achieve this optimum? Right? So that's the work of a data scientist. To achieve this optimal output with respect to the data, that your learning is proper and your training accuracy is good, your testing accuracy is good, your model is performing good on any unknown data, is what is the task of a data scientist. Just give me a second. I'm just getting a quick call. Okay, so this is how it generally works, right? So let me clear this off. Okay, let's go back. Yeah. Then, so if I have to standardize you that what is my standard machine learning pipeline. So now we have understood the training and testing concept. We have understood what is the model part of it. We have seen the EDA part of it. So what is my pipeline? So the moment you are given a data, what is the pattern that you have to follow? So let's say these are your input data. Okay. So this is your input data. So the moment you get your data, whatever business data set you have, like I've given you for the exercise, right? I've given you the data set of some housing or something. I just am going to, so that data is your raw data, right? The moment you get the data, what do you do? Your first step is to prepare your data. So whether it's an image or a text based on which you do a data preparation, you understand the data, you do all the EDA. This is your EDA portion to make your data preparation. Then comes feature extraction, which we will learn not as of now. It might be a little difficult for you, but yes, we'll see later. So we do a feature extraction after the data preparation. And after it is ready, I send my data into the model. So here I have my model training, here I have my model testing. So entire data then gets divided into training the model and testing the model, and this is my overall mood or the accuracy model. So this is my overall model to which I divide it into training and then I test it. And once I train it with the test data, I make the predictions, whether it is yes or no, whether it is good or bad, whatever it is. So this is the generic pipeline that you follow with respect to your machine learning. So you have the data, you prepare the data, you do a feature extraction, you send it to the model, you train that model, you get the test data, you go and make predictions. So that's your output. So this is the entire flow of a machine learning exercise as a data scientist or an ML engineer, whatever you can call it. All right, so let's see. I think we're with this we'll conclude. Yes. So now if I see the overall pipeline of machine learning, right? So as I've just shown earlier, what we do. So we have the input data which you receive, then that's how your production pipeline works. Okay, you have the input data, so your business data are coming, so your data gets directly applied to your machine learning algorithm. Your algorithm makes a prediction, and then your prediction gets evaluated whether it is correct or whether it is wrong. So if it is correct, it is fine, it goes for further utilization. If it is incorrect, you train the machine learning algorithm again, right? So generally what happens, your input data goes through data preparation, goes through feature extraction, and then gets trained. Once it gets trained, it makes a prediction. And once it makes a prediction, you tell whether it is a good prediction or a bad prediction. Now, in case of a bad prediction, You take this data once again to train the model once again. You train the machine learning algorithm and get the model. Okay, and this model is nothing but again then passed on to your data to make prediction, and then again check whether it's a good prediction or a bad prediction. So this is the entire cyclic flow of how your machine learning pipeline works. Any questions on this, or Kevin, or it's self-explanatory?
Explains itself.
So this is how it goes. So every time you put a model to your production, you will have your inflow data which is coming. So every time we don't train the model. So this piece is not done every time. So this is the task of a data scientist when he develops the solution. The moment he is developing the solution and he is implementing it, that means the moment it means that only the original data will come, which will go which will undergo all these steps, and it will directly make a prediction, right? And then this prediction would go for an evaluation. So every time this machine learning algorithm goes through these steps at the back end, an end user will never know it, right? So let's say you do a Google search, right? The moment you type a text is your input data in Google. So automatically this input data goes into the Google's machine learning engine, and it gives you the output. So it goes through all these machine learning exercises and then makes a prediction, which is your output, and displays your output in the console or in the web page. See how fast it is. Like if I type what is United States, I get a response quickly. So how efficient and faster Google's engine would be, right? But the overall machine pipeline of ML is this one, right? All right. So I think, yeah, with this, we are good for today's session. So any questions on whatever we have learned? Is it clear? Something new that you got to know? How's it?
Well, all that was new, but yeah, I'm learning a lot. Training data, testing data. That was the part I was struggling with, but now I kind of understood the second time you explained it. Yeah.
Okay, yeah. So, anyways, you have to go through all these concepts. So, when we go into the hands on part again, once we go through the theories and see what exactly happens, at the testing training, it's very, it's very deep. It's from here, it has to be very deep. All the easy part of the course is now gone, right? So all these are core ML concepts. So it might take some time for you to understand and adapt and adjust. But yes, as I say, you have to spend time within yourself, to go back and see whatever was being delivered to you. Take some additional material. I will give you some. Anyways, you get this material. I give reference links where you can learn more about it. You can Google any specific concept you want to know more. Everything is there in YouTube. But see, these are the ground foundation of ML. So if you make it more perfect, you can solve some. I show you the use case of rain sound detection, correct? This detection of a species sound the other day. See, these are all high level analysis of data. Who would have imagined that there will be a sound analyzer which will be kept in forests, which will capture the noises of different birds and the species, and that data can be eventually analyzed and find what are the birds which we have making sounds in that specific you know noise sound that you play, right? So see the amount of progress of machine learning data science. It's going beyond, but the ground rules are this. So the more ground is strong, the, you know you when you see a 100 200 storage building, foundation needs to be pretty strong, else your top floors will collapse. So these are all your ground rules of ML, right? Slowly you get to learn the advanced part. So we'll see more things, whatever we are talking about: underfit, overfit, how to achieve this optimal output, you know how do I validate, how is this test in training created. There are multiple ways to create it. What sort of rows should I pass into training, what sort of rows should I keep it for testing. All these things are there. It's universe. So whatever you are learning here, it's pretty new. So only thing you can easily utilize and learn it is So if you spend some time after the sessions or whenever you are free and go through the topics, Google and see more videos and learn, so some concepts you might not be able to understand by reading a doc, so you can refer to a video in YouTube where somebody is explaining you like the training and test data. So suddenly a thought came that I should give you that example which can make it clear. So like this, conceptually it has to come. So that's how it is. But these are the very basics, right? So, have you seen the assessment? I think you have completed the online assessment. I've got the mail. So, anyways, I'll check it, uh, and that's good. You have completed it much before. I have to evaluate the answers though. But yeah, uh, and I have given you the case study as well as an assessment, right? So, have you seen the data? Have you seen the notebook that I've shared?
I've seen the notebook, but I haven't had a chance to go through it yet. I was planning on that this weekend.
That's fine. You can
So
take your time. So I think you have time till how much? 12th or
11,
something?
11, 11.
Oh, okay. 11th of Feb, is it?
Yes.
Okay, that's fine. So I've given you a strict timeline first because I want you to be in that zone and spend time and do it. But yes, that I mean, little 1 and 2 days buffer I can allow you later, but it has to be stringent, not always, because if you lose that zone, then it becomes tough. Because if you don't complete this, then see how deep we are going. So if I give you one more assignment after two sessions, you're piling it up. You know.
Yep. It's true.
So the purpose of giving you hands-on is to that you do a research and you learn how to code. That's the main intention. So what I've done is I've given you questions with each cell. If you open the notebook, you will see I've given the question and I've kept the next cell empty. So you can logically develop the code. So whatever is the question, the next cell you write the code and you just execute and keep the output. All the graphs and everything that appears. And you send me the executable, IPYNB file over mail. I'll download and I'll keep the data and I'll run your code in my system and see if it is executing properly. Ensure it's bug free. Okay.
Okay.
All right. Perfect. Then I think you'll be heading towards your flight and everything. So hope you have a good journey there. We'll catch up. So you'll be available tomorrow, right?
Yes, tomorrow I'll be available. We can do it the normal time, 9 to 11.
Okay. Perfect. Okay. Great. Then we'll catch up tomorrow with the normal time. Yeah.
Thank you, Paul.